Namaskaram. In this session, we will discuss quotient ring and its related properties. Consider a ring R together with the two operations, and we know that since R is a ring, it is a abelian group under addition. Okay. Next, we consider an ideal I. I should be a subgroup of R. Since R is commutative, every ideal is a normal subgroup of R under addition, right? So we can define the quotient group. So we define R by I, and also we know that this quotient group is a well-defined group under the addition. What is addition? We have seen that the elements of R by I is of the form square bracket x. They are cosets. And what is the definition of this coset? X plus I. Okay. Also, this R by I is a group under addition. Addition is defined by coset x plus coset y is defined as coset corresponding to x plus y. This is a well-defined operation. Since R is abelian, this R by I is also abelian under this operation, right? Because y plus x is equal to the coset corresponding to y plus x plus y and y plus x are same since R is abelian. So to construct a quotient ring, we have to define one more operation on this set. So that is defined as like this: coset x into coset y is equal to coset corresponding to xy. Next, we have to show that this definition is well defined. That means coset x is equal to coset x dash and coset y is equal to coset y dash. Then coset xy is equal to coset x dash y dash. Okay, for that we have to prove that xy minus x dash y dash belongs to I. Okay, that is because we have a result. Two cosets are same if and only if x dot y inverse belongs to I. Here this dot is the group operation. Here the group operation is addition. That's why we replace this dot y inverse by x minus y belongs to I. Okay. So this minus y is the inverse of y under the group operation plus. Consider xy minus x dash y dash. We just subtract xy dash and add xy dash and just rearrange. After the rearrangement, this is equal to x into y minus y dash plus y dash into x minus x dash. Okay. Also, already we assume that coset x is equal to coset x dash. So, two cosets are same only when x minus x dash belongs to I. Similarly, y minus y dash belongs to I. Okay. Also, we know that x belongs to the ring R. So, since I is an ideal, x into any element of the ideal belongs to ideal, right? So, similarly, we can easily show that y dash into x minus x dash also belongs to I. So, these two elements are belongs to I. So, their sum is also belongs to I. That's why this difference belongs to I. Since this difference belongs to I means the corresponding cosets are same. That means coset x into coset y equal to coset xy is a well-defined operation. So we can say that R by I is a ring under these two operations. That ring is called quotient ring. It is clear that coset x plus coset 0 equal to, by definition, coset x plus 0 and x plus 0 equal to x. So this 0 is our identity under addition. And what is the identity under multiplication? That is coset 1, because coset x into coset 1, by definition, that is coset x into 1 is x. Also note that coset x is equal to additive identity in R by I. And we know that additive identity in R by I is coset 0. That means coset x is equal to coset 0 if and only if x minus 0 belongs to I. X minus 0 means x belongs to I. Okay. We know that Z is a principal ideal domain. That means every ideal of Z is principal. Okay. So we consider an ideal of Z denoted by like this, because every ideal is principal. Okay, corresponding to a natural number D. Then two elements x comma y belongs to Z represent the same coset or same element in Z by dz only when their difference belongs to dz, right? Because our ideal is of the form dz. We know that ideal generated by D is exactly dz, right? So two cosets are same if and only if x minus y belongs to dz. D should divide x minus y. Also, we have seen that z by dz can be identified using the cosets 0, 1 to up to d minus 1. Okay, for example, we consider Z by 6Z. We can identify the 6 elements in Z by 6Z using these cosets. And what about sum of these two cosets? That is equal to coset 8 by definition, and 8 is equal to 2. And similarly, by definition, this is equal to coset 12 and is a multiple of D, so that is coset 0. Okay, next result is, suppose that D is a positive integer, then the group of units Z by D Z star is an abelian group with the phi of D elements. So first we are going to establish that a coset X, that is X plus DZ, is a unit if and only if GCD of XD equal to 1. Okay, so consider the first part. Suppose GCD of XD equal to 1. Then by extended Euclidean algorithm, there exists lambda and mu belongs to Z such that lambda X plus mu D equal to 1. So the corresponding cosets are same. The coset lambda X plus mu D equal to coset 1. Decompose left side using our coset addition. So this become lambda X plus coset mu D, and again using our coset multiplication, this lambda X becomes coset lambda into coset X. Here mu D is a multiple of D, so this coset is exactly the coset 0. So LHS become coset lambda into coset X, that is equal to coset 1. So we can say that X is a unit. Conversely, we assume that X is a unit in Z by DZ. We have to show that their GCD is 1. Since X is a unit, there exists an element coset lambda belongs to Z by DZ such that product of these cosets is equal to 1. Right? By definition, product of these two cosets is equal to coset lambda X. So coset lambda X equal to coset 1. Two cosets are same means lambda X minus 1 belongs to the ideal DZ. Lambda X minus 1 belongs to DZ means this is a multiple of D. That means there exists a number mu belongs to Z such that lambda X minus 1 is equal to mu D. That means lambda X plus minus mu times D equal to 1. So we can say that GCD of X and D is 1. So now we know that a coset X is a unit if and only if GCD between X and D is 1. Okay, so we know that there are only phi of D elements which are relatively prime to D. So the size of this group is phi of D. Okay, next results. At n belongs to n, then Z by NZ is a quotient ring. Quotient ring is a field if and only if n is a prime. Also, we have to show that if n is a composite number, then the quotient ring Z by NZ is not a domain. That means we have to show that this ring contains zero divisors. We have to show that this is a field. So field means every non-zero element has a inverse. That means every non-zero element is a unit. And how many units in Z by NZ? That is phi of n. And every element except 0 is a unit means this phi of n should be n minus 1 because this set contains n elements. And we know that phi of n is equal to n minus 1 if and only if n is a prime. If n is a composite number, then we know that n is equal to AB, where A and B is in between 1 and n. This means that the coset A is not equal to 0 and coset B is also not equal to 0, but the product of these two cosets, that is equal to coset AB, and AB equal to n, and coset n is equal to 0 in this set. Okay, for example, you consider Z by 6Z. Coset 2 and coset 3, they are not equal to 0 coset, but the product is coset 6, which is 0. And the field Z by PZ is denoted by FP.